Dr. Gold in the lab, Twitch stream glowing, formulas flashing, minds wide, knowledge flowing, equations on the board, numbers never sleep, teaching math and physics while them haters count sheep. Actual education, tune in and get schooled, flipping textbooks, breaking all the rules, from Newton to Einstein, concepts elevate. Keep the stream, it's the key to our fate. Dr. Gold dropping gems, knowledge raining down, actual education making scholars all around. Perpendicular minds, angles sharp as ice, maths and physics, yeah, the future's real nice. Got the Pythagorean triangles about to flex, quantum theories on deck, breaking all the specs, relativity theories, worlds getting small, grasp the universal laws, standing tall. From the atom to the cosmos, we rolling deep, grazing up the stars, no time to sleep. Black holes and supernovas, concepts we unfold, brain power heavy, yeah, that's Dr. Gold. Dr. Gold dropping gems, knowledge raining down, actual education making scholars all around. Perpendicular minds, angles sharp as ice, maths and physics, yeah, the future's real nice.
What's up? How's it going? At what point has the stream actually started? You can ask questions during the starting point. It's okay. All right, let's get this open. What's up, Chandu? I think you came by during greed. Well, it's okay. Greed for knowledge is fine. I think Chandu, you came by earlier this morning when I was teaching physics. Yeah, so I live stream. I'm teaching physics online at UCLA this summer. Very sorry. Okay. Sensation chill dog, please. Anyways, yeah, I'm teaching a class at UCLA this summer. So, it's online, so I live stream the lectures as well on Twitch if people just want to like watch along. I can't really interact as much during that chat because I'm having to work with the students in the other chat. But you came to the right place, Chandu. This is the stream for whatever other questions you want. Let me make sure I'm sharing this correctly. Paul Erdos did amphetamines, not saying to do them, but he definitely did them and it helped a lot. Oh man, you guys. Yeah, I never wanted to get myself hooked onto Adderall or like to know what the effect, basically to know what my potential would be with like a crutch, such as like prescription pills and things. I think it's bad. No. Also because those things have side effects, and the issue is that if you become reliant on those things to perform at a certain level, eventually the side effects start building up, and those can be pretty bad. An interesting thing is that you always build up tolerances to things, so you start needing more and more in order to get the same positive effect, but then the negative effects compound. And so I always say that doing things like Adderall or whatever to study is like taking out a loan. You're eventually gonna have to pay it back. So your body remembers. You're basically like overclocking your body to try and think. So I wouldn't do it. Mix them with roids in your cereal. Sensation, if you were on roids, dog,
emotional damage,
you would look a little bit different. Just to say. Chandu says, I'm not a student or anything. I'm trying to get good solving problems, especially LEET code. Wait, LEET code? Wait, like 1337 code? Is that what we're talking about? Wait, is LEET code a thing? Sorry. I know like LEET speak, right? Like this is LEET speak. What is LEET code? Excuse me? Sounds like a joke. LEET code. Oh, it is a programming. That's hilarious. They call it LEET code. I do need to drink some water. Thank you. You highly recommend it? Nice. I'm glad that they call it Lead Code. That's actually quite fun. What's up with my chat? Anyways, one sec. Let me get my web browser to work correctly today. It gets mad when I have multiple browsers. Okay, there we go. Cool. It is not for beginners. Oh, maybe. I don't know. Could be. I will say it's not as much for beginners because I see like actual code here and not just connecting cute little wires to things. So. Alright, Sensation. It's okay, dude. We don't need to be like swinging our e-dick around with like, I know how to code, you don't.
Oh no.
That's okay. But yeah, it looks like it is at least it says prepares candidates for technical interviews. This is cool. Questions of practice. Yeah. I think I would say it's for intermediate people. Like really, really basic coding would probably be like Code Academy, right? Yes, I know, Sensation, but you know, it's okay. We get older and the terms that we use for like beginner or advanced like start to change. Code Academy I feel like is more chill. Actually, it kind of looks like less chill, honestly. Wait, what's like a really, really chill coding thing? What's called Scratch? Yeah, there we go. Scratch coding. That's very basic coding. That's what I would say is basic coding. Yeah, and it's block-based coding. That's cool. Like anything, I hate elitism in things. And I think anybody should be able to do anything at any level. As long as you're interested in what the topic is. I don't give a fuck like whether it's advanced or not. Like, as long as you're interested in it, that's way better than probably 90% of the population that, you know, just wants to watch TV all day. Myself included sometimes. I have to say, I had like, a friend had a birthday party, but he had his birthday thing be like a 48-hour birthday party. It was like there was a Friday event, there was a Saturday event, and I'm like, man, you get one night for your birthday. You don't get 48 hours. As you can tell, my voice is basically gone because, yeah, it's just partying for 48 hours. I was like, Sunday I had to just basically be comatose and just watch TV. I hated it. Rascals, I hate Scratch. If you're over 13 to 14, Scratch is overrated. Under 13 to 14, Scratch is valid. Yeah, I agree that, like, I don't think coding is going to die in the same way that, I don't know, let's define the term die. Is it going to be something that pays a lot of money for humans to do? No. Not anymore. Yeah, I will say, like, straight, just like regular coding that was usually shipped overseas to India and wherever, that is gone. That whole market has been demolished by AI. I agree with that. But I think learning to code and learning how to code is still an incredibly valuable skill. In the same way that we used to have people literally run to deliver messages, right? But did the invention of the carrier pigeon or the invention of the telegram, did that like destroy running? I mean, it destroyed running for money. So, you know, you no longer need people to go deliver messages. But the act of running still builds up a lot of strength and skills to do other things. And in the same way, I think learning how to code is invaluable for building up skills on how to logically solve problems and, I don't know, just like pattern recognition, algorithmic thinking, recursion, object-oriented programming. These are all very cool concepts that apply to other problems that you need to solve in life. And the only way to get good at those is to practice using those skills at something such as coding. And it sounds like Leet Code is kind of a playground for that. Think of it as like a gym, I guess, right? You go to the gym, they have a bunch of weights you can lift, they have a bunch of challenges you can do. Sounds like Leet Code kind of provides that same kind of like coding gym thing. Yeah, actual software engineers are definitely still getting hired. Yeah, for sure. That's software engineering. That's different than just being a coder, like just coding. And I would argue that in order to be a good software engineer, you do need to know how to code, because you have to be able to read something and like kind of diagnose it, or at least understand what the structure is, so that you can come up with the big like game plan for what needs to happen. And as I'm finding out with my textbook platform, this course, just vibe coding your entire platform is a fucking recipe for disaster.
Oh no.
I'm so frustrated with how many times I have students email me and saying like, none of my answers saved, or all my questions got erased, or I'm seeing twice the amount of questions. I'm like, man. LLMs are not the new industrial revolution. It's unsustainable and just shite. I think the rate at which we're doing things is probably unsustainable. I don't think LLMs are ever gonna like fade out. I don't think it's like NFTs where people are like, are you dumb? Like, what is this stuff? Like, AI is still very useful. LLMs are still very, very useful. And I think they will continue to be useful. I think the expectations that they're supposed to keep on this meteoric exponential rise in capabilities and doing things, I think that is unsustainable. And unfortunately, I think that's where the money is. The money's going into like prospecting on this. So, what's up, Femvox? It hasn't changed since the 80s. We didn't have the hardware capacity to run AI until now. I don't know. I feel like a lot of stuff has changed pretty rapidly, man. Its integration into everything is pretty crazy. Yeah, there's Moore's law as well, right? Yeah, hardware will hit a wall. We can only make transistors so small, right? I think we're to 3 nanometers now. Are we at the 3 nanometer process? Yeah. I remember when like 7 and 9 were like the huge accomplishments for the whatever CPU architecture. I think we're down to 3. Eventually, you start hitting the wall of physics, which is, by the uncertainty principle, you can't have things below a certain size. Otherwise, like quantum effects start to like take hold. Yeah. I think we are seeing a rapid change in the atmosphere and the adoption of technology, for sure. In the same way that, I mean, would you argue that the cell phone is like the industrial revolution? Because like technically, well, we've had communication devices, we've had ways to send messages. But I would argue that the introduction of cell phones has probably changed the world an insane amount, probably on par with the industrial revolution. And I'm not sure I'm going to say for the better or for the worse, but cell phones are more like a black plague than an industrial revolution. I know. Yeah, that's what you can say. Anyways. I don't know that a smartphone is inferior to a phone, though, Sensation. I can't, like, read my emails on a phone. I can't take pictures with a phone. I can't share those pictures with a phone. I can't be watching my stream right now on a phone. On a smartphone, I can. Everything in a phone is inferior to its derivative technology. Okay. I love this, like, philosophical debate of things. All right. So yes. This week is my second to last week of teaching at UCLA. Good job. I recognize I have been pretty absent in Discord for the last 4 weeks, and I apologize, but yeah, this UCLA course has taken a lot more of my time than I expected it to. Definitely more time than it did last year. And that's due to a lot of errors in this learning platform that I'm using. So I got one more week here, and then another week, and then I'm done. I have to grade, so I might need like a couple days to like grade exams. But after that, we can go back to, you know, our regularly scheduled programming of office hours and fun and like chess matches and games and things. I appreciate you guys sticking around while I do this. The summer's always kind of this is our 5th summer I've done. It's my 5th summer of streaming, and the summer is always kind of a weird time because not many people are looking for help with homework, which is what we primarily help out with. And so I've always like come up with like different things to like keep people involved. One year we did like an SAT studying course. That was fun. We've done summer camps a couple years. I was going to do it this year, but man, dude, I just got overwhelmed. I just couldn't. I just can't. I literally just don't have the time. But yeah, August 1st or July 31st is the last day I'm teaching at UCLA, which will be bittersweet and fun. And then after that, I got like 3 or 4 weeks before I head off to Burning Man. So maybe we'll do like a fun little mini tournament for August, because I'll be done with UCLA. I won't have to deal with any more like coding issues and bugs. So also tomorrow, office hours will be much earlier. I got invited to go to the AAPT meeting, so it's the American Association of Physics Teachers. Pretty cool. Usually it's like a $400 ticket, but because I teach physics, and I know some people that teach physics, I got invited to this. And it's in my backyard. It's in Pasadena. I live in Los Angeles, so I am going to go to this tomorrow after my lecture at 2 o'clock. So I will not be able to do office hours at our normal evening afternoon time, because I will be at this conference seeing a bunch of other physics teachers and what they do, networking and stuff. But we will have office hours an hour earlier. If you want to see the time I'm going to do that, we always have our calendar at actualofficehours.com. Go to the streaming schedule, and there it is. There's our new office hours time for tomorrow, because then I'm going to the meeting in the afternoon. Brasco says, I just don't like it because now I have to hear dumbass teens who spend their entire day locked in their room watching TikTok say stupid shit like 6'7". Oh man, it's okay. We did pretty dumb shit too when we were their age. I just don't think it was as broadcasted. It wasn't like people heard about it, but it wasn't as easily viewable. I definitely did some dumb stuff as a teenager. No philosophy, just an unk-like hatred for what the youth find funny for some reason. We also found like pretty dumb stuff funny. I like when you said, Bresticles, that our brain rot used to have, what was it, culture, or it used to be more smart. I forget. There was some word you used for like the memes, or maybe it was the memes. The memes used to be a lot more clever back in like the 2010s for sure. I will agree that some of the memes in today's like brain rot culture don't make any sense at all. They're just ridiculous, and the reason they're memes is just because they're ridiculous. But then again, I mean, we had I Can Has Cheeseburger. Like, why was that funny? This is like one of the OG memes. Yeah, which then spawned the occurrence of Catterday, which was Saturday. It's like, it's Catterday. You got to post cat pics. So I don't know. Yeah, we also had like some kind of like dumb things. That's okay. I think the difference is that the older generations didn't have to hear as much of it from us, because it was kind of like our little space. Like, they weren't really plugged in or tuned into it. Nowadays, everyone of all ages is connected on social media, the internet, or whatever. So everyone sees everyone's shit. And I think that can probably be a little overwhelming and lead to cynicism and rebellion and, I don't know, counterculture, whatever you want to call it. It used to be, I think, that like every generation had their own little counterculture, but it wasn't as prevalent to the other generations because there wasn't ways to share it as easily. Nowadays, things just go viral and they just hit the internet, and now, you know, Cheryl, who's like 65 or whatever, is seeing the same stuff that, I don't know, Hayden, who's 13, is. And There's just a disgust for each other's cultures. It's not even a youth thing here. The only youths that like that stuff wear tracksuits. I don't expect you to know exactly what that means, but it's not good. Yes, we know what the tracksuit culture is. Yeah, the Italian brain rot doesn't even have a reason. It is, the Italian brain rot is funny though, because at least it sounds Italian, right? Ballerina cappuccina, and then like it sounds Italian. I don't know why it's called Italian brain rot, other than it's sounding Italian. I don't know if it actually originated in Italy, but they are like really funny AI generated images. I put them in my, so they were very popular last year for sure. Italian brain rot had like a big thing. Definitely in the spring, because I put a lot of them into my physics clicker questions. So the questions the students would answer like during lecture, just to like, you know, to add some humor and to add some relevance. People are more likely to listen to you and learn from you if you speak their same language. You can argue that their language, you know, sounds very degenerate, or it doesn't even sound like English or like whatever, and kind of be in disgust of it, but then they won't listen to you. They won't learn from you. I think that's actually one of the big core philosophies I have of this nonprofit and this Discord and this Twitch and everything, is that I don't want to ever become the grumpy old man who refuses to accept the culture of those that are coming up at younger ages and learning, because then they won't listen to us. You have to speak their language, even if it's a language that you think is, again, like a bastardization of English. Like, it doesn't matter. You have to still get through to them. And the only way to get through to them is to speak their language. So I will adopt sometimes these like cringy or nonsensical memes, because it's the gateway into getting that generation to also listen to you when it comes to, hey, like, should I take math classes, or like, is physics cool, or why should I learn biology? Otherwise, I don't know, you become unk that no one wants to listen to. And what's the point then? I could just go to a dive bar and just go talk to people my own age and bitch and moan about like society, but that wouldn't be helping anybody. Yeah, kind of funny, kids. Now we're running over saying Skibidi Toilet. Skibidi Toilet is old, by the way. Skibidi Toilet is dated. Skibidi Toilet was like Gary's mod from Half-Life, funny enough, like about 2 years ago. Yes, they would be institutionalized. Yes. Well, it's our job. It's our job to try to improve their intelligence. And sometimes that means speaking their language. So that's my philosophy. All right. I don't have any questions from the physics kids, so let's see what we got on the queue from last week. Some stuff with tons of views. Oh, yes, there we go. Help, please. Yes, this question. This is kind of a good one. Thank you for submitting this help, please, by the way. Sorry for if you had to listen to me rant for 20 minutes. This was an exam question, actually, that came up on my exam that I gave out. So let me do this. Okay, a cube with a unknown density rho naught is placed in a jar with two different fluids or densities. The cube is at rest. One of the fluids has a density of that, the other has a density of that. The heights of the locations are there and there. These are the randomly generated numbers that should have been the same before and after on Kudu, but for some reason they weren't. Like, for some reason the numbers that students saw when they took the exam was different than the numbers they saw after they took the exam. I don't know why that was. It's really dumb. Also, wait, why is this not displaying the right thing? It's not displaying the right chat. One sec. I gotta fix this. Chat separate? Is this what I call it? No. Oh, yeah, there we go. Why is it capturing there, though? That's wrong. What the hell? Wait a minute. That's capturing correctly. Yeah. This is not. Oh, maybe let's just turn this one off. There we go. Okay, sorry. Sorry, now that's correct. Okay, good. All right, we're good. I think we're good. No. There we go. That's what I want. Okay. Let me put the numbers for things real quick. So this is going to be 13.8. And then B is going to be equal to 17. And then C is going to be equal to 20.3. All right, first question asks, calculate the density of the cube, rho naught. All right, so we know that this cube is at equilibrium. It's floating. So we want to think about what the forces are on this cube. Okay. So I know I have, for instance, the force of gravity that's pulling this thing down. And that's going to be equal to rho Vg. Okay, cool. Because that's mg, pulling it down. And then I'm going to have the buoyant force pushing it up. Now, this fluid is partially submerged in two different liquids. So technically, it's going to have two different buoyant forces. It'll have the buoyant force due to the blue liquid for this amount of volume. And then it'll have the buoyant force of the gold liquid for this amount of volume. Okay, so we're gonna say there's two different buoyant forces. There's gonna be FB1 and FB2. Okay. And this we said, okay. This was rho 1, which is 671. And then this is rho 2, which is 1270. All right. So rho Vg down there has to be equal to, let's do the first buoyant force. So buoyant force is equal to also rho Gv, but it's rho Gv of the fluid. So this is going to be rho 1 Vg. And this is going to be rho 2 Vg. But then V refers to the volume of fluid it's displacing. So in the case of here, this is like V total. So for the cube, it's the total volume of the total cube. So that's going to be, and then did we say, well, we're going to figure out rho. Okay, so this would be rho. The volume, because this is a cube, is going to be length cubed or height cubed or whatever this dimension is cubed, which in this case would be 17 minus 3. And then, sorry, this is also in centimeters. Okay, so we have to be clever here. So this is 0.17 minus 0.03 cubed. And then this is times g. All right, now let's do the buoyant forces for the other ones. Okay, so for this one, this fluid, we're going to look at this amount of volume, which is going to be 17 minus 13.8 for the height, but then like the depth and the width of the cube is the same as it was here. So this is, for instance, the same dimension for the width and the depth of the cube. So this is going to end up being rho 1. We'll say this minus this to get that length. So that's going to be 0.17 minus 0.138. And then that's going to be times g. Well, sorry, volume, right? So volume is going to be that, and then times the other dimension squared. So 0.17 minus 0.03 squared. Okay, and then this one will be rho 2, And then that amount of volume of liquid that's displaced is 13.8 minus 3. So I'm going to say 0.138 minus 0.03 times the other length times depth, which are the same, which is 0.17 minus 0.03 squared. Put the square outside. There we go. So now I just need FG to equal FB1 plus FB2. And so that's going to be rho 1. Here, I'm just gonna copy all this. I don't have to like do it all again. There we go. So that's FB1. That's FB2. What's up, Nerduino? Good to see you. Oh, Nerduino, I was just saying, I am going to go to this meeting tomorrow in Pasadena for AAPT, American Association of Physics Teachers. I'll be there tomorrow at like 3 o'clock up until like, I want to say like probably 6 or 7. 6, 7, as the kids say. But if you're in the area, I'll text you. Maybe we can grab dinner afterwards or something. I know you're like kind of close there. Okay, and then FG would be rho times 0.17 minus 0.03 cubed times G. Does that make sense so far? Important thing was getting the two buoyant forces and then setting it equal to the force of gravity. Yeah, okay, cool. Enjoy the beach. I saw some funny meme the other day where it said, you live in California, you see the ocean, you're so close to the ocean, but you only go to see the beach like once a month. Like, it's so true sometimes. What's up, Jack? Dun. Okay. Nice. Okay, so then the final part to solve for this is move this over. And you're left with this. Don't get sunburnt. Yeah, I always get sunburnt. All right. There we go. That's that. All the G's cancel. And then we're going to divide that by 0.17 minus 0.03 cubed. And then you're done. That should be it. I'm not going to plug this all in a calculator. That would take forever. But I'm pretty sure that's how you do that one. We were doing one of the previous exam questions, Jack, here. Someone was asking.
Okay, I was actually going to ask about that one.
Oh, cool. Do you have questions about all of the parts, or which ones?
So, part A, I got part B and part C correct.
Oh, good.
Yeah, hold on. Let me double check. Yeah, I got those parts correct. But part A I got wrong because, well, I made an assumption that, so when I was making my diagram of this problem, I added in things like, let me see. I need to reread my work.
You're okay.
I had in my free body diagram and stuff when I was working it out that there should be a force from the body. Okay, let me read this.
You're okay.
So the problem mentions that there is like two liquids, right? Our cube is
it's midway, or not midway, but you know, it's partially in this one and it's partially in this one, correct?
Yeah. And in question, or I guess part 2, it mentions that it's like open to the air.
Yes, this is open to the air, correct.
So whenever I was doing this problem, I figured that, okay, I must have the force of I have one force buoyancy, then another force buoyancy.
Good.
And I have the force of gravity of the cube.
Yep.
But then I thought, shouldn't I have a force of like the weight
atmosphere
of whatever the first density, the yellow liquid on top of the cube? Then shouldn't I also have some sort of like force generated by like the pressure of the atmosphere? Because because I was like thinking to myself, well, if it's open to the atmosphere, which is, it says in part 2, I was like, okay, you have a set pressure, and I don't know the total area of the top of the cube. Not cube, but like the
Right.
body of water or whatever. But I was like, okay, any pressure going through this liquid is going to end up hitting the cube on its horizontal surface. And
Yep.
if it's a cube and I know the side lengths, I'm like, oh, okay, I have an area and I have a pressure. Bam, that's a force. So should I not have assumed that?
Yeah. So when this one was strictly dealing with Archimedes' principle, right, which has to deal with what's the buoyant force of something, and I agree. You start saying like, wait a minute, but if I think about it in terms of pressures, don't I have pressure from the atmosphere pushing down, right? Well, that atmospheric pressure from the top contributes to the pressure here, and it also contributes to the pressure here. So it technically cancels out because the atmospheric pressure provides upwards force here and it provides downwards force here. And it's the same from the atmospheric component.
Okay. Well, so,
So here, if we want to think about Archimedes' principle, right? Or let's just again look at, let's say for instance, some amount of fluid here, right? You're gonna have the side forces, right? Which we don't care about those because those cancel out. But let's look at the top and the bottom. So you are right that F is equal to PA, right? And that comes from pressure is equal to force over area, right?
Yeah.
Okay, great. So if we were to calculate the pressure here versus, let's say, for instance, the pressure here. Here, pressure would equal to pressure atmospheric, right? Plus the amount of fluid that's above it, right? And that's the rho GH, let's say rho GH1 times A.
Yeah.
Okay? Or just rho GH, sorry. Let's just calculate pressure for now. So that's P1, yeah?
Mm-hmm.
The pressure here, which points upwards because it points normal to the surface, right? That it's in contact with. So at the bottom of the cube, the normal to the surface, right, is pointing up. The pressure, the force points into the thing, into the cube. That's also going to be pressure atmospheric, but now it's plus rho GH2. Okay? So if I want to calculate, do you see how like this will basically cancel out when I do like...
I see how that cancels out. I need to look at the problem. Were we measuring to find the pressure at the top of those? Or just like, well, let me double check. I have it open.
So for part A, you're not calculating any pressure at all. You're literally just calculating forces.
The density. Okay,
Yes.
that's right.
The reason why in part 2 I have to say open to the atmosphere is because when you're thinking about now fluid is leaving here, I have to consider the pressure from the atmosphere. Is it able to affect the liquid here, or is it only affecting the liquid on the outside? That's why I put it in part 2, really.
Okay. So my understanding is whenever the pressure from the atmosphere is acting on the top of the open liquid, that pressure is going to act throughout the entire cube.
Throughout the entire liquid too. Yeah.
The entire liquids.
This is another principle. I forget whose this is called, but yeah, anytime you add pressure somewhere in a liquid, everywhere in the liquid also experiences that same increase in pressure.
Okay, that's why it cancels out in all directions. Then why did we not count the weight of whatever the density of that yellow liquid is on top of the cube?
Oh, on top of it. Yeah. Because the let me think.
Because I mean, I think you gave us a value for like the actual density of it, and I mean, if you subtract like the gap between B and A, like you could theoretically come up with a volume to well, I guess.
Yeah.
You could. I guess you couldn't come up with a. Well, I mean.
No, you can't because.
Area.
No. You know it's a cube though, right? You know it's a cube. So you know whatever this dimension is the same dimension as the depth of it, and also the same dimension as the width. The only thing that's changing is the height. So you can get the volume. You can definitely get the volume here. It just ends up being that it's that B minus A, then times the other term squared. times whatever this L is. So remember, right? Volume is equal to length times width times height. These two things are always the same in our situation because it's a cube. And the height of the, I guess, rectangular prism in this case changes based on like what height cross section of the cube you're looking at. If you're looking at the whole cube, then length and width and height all equal each other. But if you're only looking at part of the cube, the length and the width are staying the same, but the height changes.
So I can
You see
use
that?
the displaced volume in that yellow liquid.
Correct. Yeah, this displaced volume is what.
Okay. That's what I did originally. Sorry, I didn't say that better.
It's okay. You can also think about like, so this amount of liquid here is like another atmospheric term, because whatever this is doing is increasing the same amount of pressure here as it is here. And as it is here, for instance.
So wait. So for that yellow liquid, that's the liquid 1. I correctly calculated the buoyancy force created by that liquid.
Mm-hmm.
But since some of that liquid is still on top of the cube, shouldn't there be, I guess, like a weight pushing down on the cube then?
No. Yeah, no, this doesn't count because this amount of, so you have the right intuition that this amount of liquid should be pushing down, but it's also contributing to the pressure at the bottom here, which is then going to push up.
Oh.
Yeah, let's say you weren't doing it by any like sort of like displaced liquid thing or whatever, right?
Mhm.
You would have if those weren't in balance, yeah, exactly. Yeah. You have this amount of fluid above, right, which is creating a pressure here.
Yeah.
And then here you have this amount and this amount adding to create the pressure here.
Yeah, you have pressure, I guess, equal on, well, would the pressure be equal on all sides? Because the yellow liquid, right? It's pushing down on the top surface and only like some portion of like the surrounding force.
Right. So the only way for this to float, right, is for whatever the force is here, and the force here, the difference of that to equal the difference of the gravitational force of the cube. The pressures aren't going to be the same. They can't be the same. Otherwise, this thing would be moving. Otherwise, this thing would be sinking also with the force of gravity. If this thing had no mass, if the cube had zero mass to it, and thus like wasn't displacing anything, then yes, the pressure here would equal whatever the imaginary pressure is here.
Okay, hold on, let me see. So back to the top of the cube, right?
Yeah.
The yellow liquid, it's a pressure. It has a density, and it has some sort of volume.
Uh-huh.
So, and plus gravity, well, the pressure times the area, which I'm just going to say is the top of the cube. So
Yeah.
the pressure of liquid 1 pushing on the top of the area of the cube, that gets you a force, but that pressure is pushing down at the same time as, or downwards on the cube at the same time as liquid 2, that cyan color is pushing back up.
Yes, at the bottom. Here, let me put this on a new page real quick, just so I can, because I think the issue is that there's 3 different regions here, right? Let's say like region 1, region 2, region 3. I know this is fluid 1, this is fluid 2, but let's just look at it from a region perspective. Okay.
Mm-hmm.
Let's think about what the pressure is here. Let's call this, for instance, like pressure top, and then let's call this pressure bottom. Okay.
Mm-hmm.
So at the top, right, you have just this amount of liquid on top of it pushing down. Oh yeah. I guess we could also call this region 4. Yeah, let's do that. Let's call this region 4. So yeah, let's calculate what the pressure, what the absolute pressure would be here, right? So pressure top would be equal to P atmospheric plus let's say rho 1 G, and I'm going to call this just like H1, for instance.
Okay.
Okay? Because you have the atmospheric pressure, and then you have the pressure of the liquid above it, and it's pushing down on there. Okay?
Okay.
Now let's look at what the pressure would be at the bottom. Okay? Pressure at the bottom, absolute, right at the interface between 3 and 4. That would be atmospheric pressure. Then you'd have rho GH1, or rho 1 GH1, right? Rho 1 GH1. You'd have rho 2, plus rho 1 GH2. So you have this height of liquid, you have this height of liquid, but they're all the same liquid 1. And then you'd say plus rho 2 GH3, which is this height right here.
Okay.
Okay. Now, notice how
You
this...
also had the pressure of the atmosphere, right?
Oh, sorry. Yeah, sorry. P1 is P atmospheric. Sorry, I did call it P1. Sorry. Thank you, Nerduino. Yeah. P1 is P atmospheric. Sorry, that's what I meant to say. Sometimes I call it like P naught or something, but yeah. Okay. Is that good so far? So we define
what I see. The pressure of the atmosphere. It's when it's all the way up top on the yellow liquid. It's going to push down, and it's just going to cancel out everywhere on the cube.
Mm-hmm.
So I still see that there is some sort of pressure being generated by the yellow liquid.
Yes.
And I do see that it's also being counted at the bottom.
Yes.
So I can see why it's counted off.
Yeah.
Then you're left with the only pressures at the bottom being the one from, I guess, the yellow liquid in region 2 and the blue liquid in region 3.
Exactly.
Okay.
Yes.
So...
And what that looks like, also mathematically, is it looks like just the, when we multiply this times area, right, to get force, it looks like the volume of liquid displaced in this second area, plus the volume of liquid displaced in this third area, and then times the different liquids that they're in for densities. Right, because when force equals pressure times area, this area is like, let's call it like length squared, right? It's whatever the depth and the width of the cube is. So now you get rho 1 G H2 L squared plus rho 2 G H3 L squared. And this right here, right, that's the volume displaced in like what I'm calling region 2, right? This region right here. And then this is the volume displaced in region 3. And then it's the volume of liquid displaced, and so it's specific to that liquid. That's why this one is rho 1, because the liquid that volume is displacing is the rho 1 stuff. And then in this case, the volume that's being displaced is the rho 2 liquid. So that's why we use rho 2. Yeah. The other way they talk about it is they say, like, what's the gravitational weight of liquid that is no longer there? And we know that, right? That's like weight of liquid. That's just equal to rho GV, which is the same thing as rho G and then H times like L squared.
Okay. I think, yeah, I definitely think I could have done what I did first was I did a free body diagram.
Yeah.
Like I kind of drew some of the pressures, but I guess that would have probably save me some time.
Mm-hmm.
Okay. Yeah, that makes more sense. Do you mind if I'll be right back, but do you mind if I take a picture of this?
Yeah, for sure. I can I can just send you the screenshot here. Well, can I put screenshots? Here, let me just download this as a PNG for you. Jack, you want this one, just this one, or you want this one as well? I'll give him this one as well. Free body diagram. Take a drink. Is that like this? Thank you, Sensation.
Thank you very much.
Yeah, you're good.
Yeah, that one was confusing. Can you go back and look at question 10?
Yes, I totally can.
Not 10, sorry, 8, I mean.
Question 8. Okay, yeah, let me do it. Here, let me... I'm just gonna put, screenshots for working.
I'll admit, this one I was incredibly stumped with for a very long time. Until
Yeah.
I messed around and realized, oh wait, it's past stuff. So, long story, what I did was, so I figured out how, I did a little trig math and I was like, okay, it's path-based. And then I noticed before that this had like positive, negative, not positive, but like constructive and destructive interference with the waves. So I was like, okay, I'm trying to solve for the vertical displacement of two speakers, and the speakers are producing waves.
Mm-hmm.
And so then I had a trig equation telling me, okay, if I want to find the vertical displacement, I have to know the length between the observer and wherever the two speakers are, which was given. And then I had to like kind of work that out. And I was stumped for a while until I just started messing around with like some of the like wave equations and frequency. Until I was like, okay, wait, if I have a known frequency and the speed of sound, I know what the wavelength needs to be. And if I'm like, a wavelength is a certain measure of like distance.
Yeah.
I'm also supposed to have a certain measure of distance from, I guess, like speaker A and B clashing to the observer. I kind of like worked out the right equation.
Okay.
But where it kind of fell apart was, so it looked kind of ridiculous when I wrote it out, but I was like, this kind of makes sense. I was trying to solve for, I got the vertical displacement to be 23.73 meters.
Okay.
That was because I put the wavelength to be, or I knew the wavelength needed to be 0.704 meters, right? And
That'll change based on what your numbers are, but yes.
oh, that was the number it gave me.
Okay.
So it's like, okay. Then I was like, all right, if I need to get a certain frequency and I know the velocity of sound, I put that in an equation and got that my wavelength actually needed to be 24.36, or not 24, but it needed to be 17.15 meters for the person who's standing all that distance away to only barely hear it at 20 hertz. So I was like, okay, that means the total distance, I just need to do the total distance divided by the wavelength number I got to get the number of wavelengths I had. So that gave me 24.36 wavelengths.
Which, okay. And then, you know for something to be a minimum, right, it needs to be an odd wavelength difference in path?
Yeah, so...
Or like an odd multiple. It needs like 1, 3, 5, 7 or something.
Yeah, I knew for like,
half,
for it to be like, well, I thought perfect perfect destructive interference was like you couldn't hear it. So
Correct.
it's like, it obviously can't be 1/2 wavelength, because that would be, you can't hear it. It wouldn't be at 20 hertz. So it's like 24.36 wavelengths. That's close to 24.5. And since 24 is an even number, I was like, you know what? Sounds kind of right.
Oh, okay. Yeah.
So
I agree that like in like, yes, a perfect world, you couldn't even hear anything, right? If it was exactly half a wavelength. But in the real world, even if something has exactly half a wavelength of path difference, there are going to be atmospheric effects. There's going to be random like wind. There's going to be whatever. Nothing's perfect. So you will hear something, but it will be the softest thing that you could hear. And that's supposed to be like perfectly destructive interference.
Oh, okay. I thought in the ideal case, perfectly destructive interference wasn't what I was like trying to go for. I was trying to find a number close to it. That's what I was doing.
Well, let's see.
Because I
Let me see how I would have done this one.
Okay.
Because you have a source from here, right, and a source from here.
Yeah. They're
And-
putting the exact identical song.
Nothing is perfect. Yeah. It's like that Rick and Morty thing where he experiences perfect level and he's like, "Oh no, I can't live anymore." Yeah. Okay. So the path difference, right? Path difference is going to equal whatever this hypotenuse is minus this, right? So if we call this like whatever, like source 1 and source 2, right?
Mhm.
Then L2 is going to equal to the square root of delta y squared plus delta x squared.
Yeah.
And then L1 is just going to equal to delta x. And so in order for there to be perfectly destructive interference, in order for them to hear the minimum amount of sound, you need the path difference. So you need L2 minus L1 to equal some odd multiple of half a wavelength. So
Yeah.
we write that as like 2n plus 1 over 2 times lambda.
Yeah, I got I got like just change in x squared plus change in y squared parentheses over 1/2 minus the just change in x. Change. Can I get change in x squared? Why did I get change? Oh yeah, it is change in x. Duh. And then that equaled the odd wavelength.
Okay.
So I got that far and I ended up getting to the point where I was able to work out my equation and rearrange everything to the point where like I had it right. But where I was wrong was the total wavelength. Because my wavelength was still like 24.36 times my given wavelength in the problem.
I mean,
And I was like, that's a pretty big wavelength.
Yeah.
But I was like,
Oh,
it's
but
close.
it's a distance though, right? You're trying to calculate the lowest height. So you're trying to minimize delta y. is what
Yeah,
you're trying
I
to do.
thought I minimized it. Like, because, well, yeah, I thought I minimized it.
Yeah. Okay, so it's because it's this, right?
Yeah.
Minus just delta x is equal to, I'm just going to say like odd number divided by 2 times lambda. And then you have values for delta x, right? So you're trying to
yeah.
solve, you're just trying to, and you have values for delta, for lambda, right? So all you're trying to solve for in this case is delta y. And so you think about this, right? This will happen when the path difference is half a wavelength, when it's 3/2 of a wavelength, when it's 5/2 of the wavelength. But I wanted the lowest height, right? I wanted the lowest delta y. And so
Okay.
the lowest delta y will occur when this number is the smallest lambda.
Okay. I
So
think
this-
where I messed up was I tried solving for a total wavelength that
Gotcha.
exactly equaled 20 hertz. So,
Uh-huh.
because I thought that was like a little like trick in the question. Like, just like off the top of your head, what is like the lowest frequency a human can hear? So, and I asked that in the Kudu, or not in the Kudu, but a campus wire, and it's like,
Yeah,
oh
yeah.
yeah, it's 20 hertz. And I was like, I think it was you or like someone else like said, yeah, it's 20 hertz. And I was like, oh, that's what he means.
Yeah, no.
And so That's what
Sorry,
led me
sorry.
to have.
Sorry, yeah, minimum sound. Yeah, I wasn't thinking about like hearing, right? What weren't referring to like what's the lowest frequency the human ear can. The lowest frequency the human ear can. I don't think I think it's like 38 hertz.
It's 20 hertz.
Is it?
I read it in the text. It's like 20 to 20,000 hertz
It is 20 hertz. Oh, okay. I just know in like audio production, no one really does anything below 40. It's just silly. It's just useless.
So that's why my odd number over 2 times.
Yes, I get you
wavelength is
now.
so fucked up.
I get you. But interesting. So wait, what did you do with this wavelength then? the one that's
I
given
did
to
that
you.
wavelength times the 24.36 because I knew I needed to get so using the frequency 20 hertz and the speed of sound, which is 343
Yeah,
meters per
sure.
second,
Right.
I got this huge, big, long distance number, which was like 17 and something meters, right? I was like, okay, that's the total distance that it should be roughly. But I was like, how do I put that into wavelengths? And then I was like, oh, wait, hold on. I know it gave me the length of one wavelength in this instance. So I just
Oh,
divided.
so then you just divided it, and then you saw like which one it was like closest to, I guess.
Yeah, and it came out to be 24.36 wavelengths, which is like, kind of, it was close to like 24 and like a half wavelengths. So I was like, oh, okay, that must be sort of close.
Right.
So that's what was my thinking, because I did the same thing on one of the homework problems and it was correct. So
Which homework? I'm pretty sure this one was also like close to a homework question.
it was.
it was.
It's the one with like the expanding freaking. It wasn't a door. It was something.
Oh, the YouTube.
Yeah, it was close to that because it was.
That was also an exam question though, right? I was
Yeah,
glad
so-
I was glad you asked this one right during office hours, because I was like, oh, this one is like exactly one of the questions.
Yeah, because in that one, it's iterations. Like you're growing, like your, I guess your path of travel, or like
Mhm.
like your path of travel, and that's what I was thinking. We're changing our path of travel based off whatever our vertical displacement is
I
going to
see.
be. So I was like, it's not that far off. And I'm like,
Yeah.
I'm sure you're going to have a fairly large number, because whenever I came out to be 23.73 meters, the distance it gave me, the change in X,
Yeah.
was like 7.8 meters. So I was like, oh, it's really big. But I'm like, it's only like 3 times as large. So I was
see.
like, not crazy. So I guess where I was wrong was, okay. I think I just made a false assumption.
Yeah, it's okay. Yeah, you thought that minimum sound was minimum frequency instead of just
Yeah, I thought you were trying to
Perfectly.
like,
perfectly
Drop.
negative interference.
so I thought you weren't asking for perfect destructive interference. I thought you were asking for like a very particular.
Got you.
Yeah, that's okay. That explains that. All right, cool. All right, well, that was fun. All right. Then, can I ask a few questions about the exam then?
Yeah, for sure. What's up?
So, so it opens on 12:30 Pacific time
On Friday.
today. It's shorter than the last exam, right? The window to work on it.
Yeah, the length of the exam is the same. It's the same 442, but the window is going to be 8 hours instead of 12.
Okay, got it. So, all right, I know when that closes for me then. Is it
Like,
going
how
to be
long?
like?
How long did the last exam take you to do? Just like honestly, I'm just curious.
It took a while. I'm not gonna lie, because
Yeah.
I was like, I think it's one. Also, this is an accelerated class. I'm like, once
This
you
is a
sit
tough
down-
class. It is. It's a very tough class, man. Yeah. Like,
Because once you sat down, I was like, okay, this looks familiar. Like, admittedly, I started with like the not multiple choice, the last 2 questions, the one that were like 30 points each. I started with those first. So I was like, I went through and I was like, what topics is this related to? And I was like, okay,
Yeah.
this one's the hardest. I should probably do this now.
okay.
So that one took a while. I also think like, obviously I made a few mistakes here and there, but overall wasn't like terrible. But I would say, I don't know how other people did, but if I were given this is like, for I guess like a midterm exam, this
Mhm.
length is like way longer than what I usually see in other
For sure.
classes. If
Yeah.
that makes
No.
sense.
In a class, you'd only get 50 minutes, and I'd probably have to cut this in half. Yeah, to be honest. for sure.
Oh, I don't know if I could. I don't know if I could. Well, I think I could finish that problem. I think I could finish the test.
Let's say, for instance, you only had to do 2, 2, and 1. So instead of doing like 4, 4, and 2, let's say you had to do 2, 2, and 1. Do you think you could do that in 50 minutes?
2, 2, and 1. 2 being multiple choice. 2 being
2 numerical, and then 1 free response.
Would the free response be the same, like 3-part questions?
Yeah.
In 50
It would be close,
minutes?
probably. Yeah, in 50 minutes.
Um,
Also, the numbers wouldn't be as terrible. The numbers are terrible because it's a relic of like in the past of us wanting to use random numbers for every student so that it wouldn't be as easy for them to like just copy numbers from other students. So like when I do in-person tests, I make the numbers nice. They're not randomly generated because I don't need to do that because everyone's in the class, everyone's sitting there, everyone's taking the exam. With the online thing, it became this whole, man, how do you like proctor this? How do you like try to dissuade cheating? And it's like, oh, well, use random numbers. But nowadays with AI, it's kind of like the random numbers doesn't even matter.
it sounds like you propose giving out the 2, 2, 1. It would be like 7 questions in total. That
Correct.
is still more than like. I mean, keep in mind, I haven't done like 5 years at UCLA, but like
Yeah,
that would still be a lot of questions for like a 50-minute exam, in my
for sure.
opinion.
Okay.
No
I
offense.
always need the feedback.
It's just
No,
like,
no, dude, no offense. No offense taken.
because like whenever I think of like taking a midterm exam, it's usually just like, in my experience, someone just does like one huge free response question and like maybe 1 or 2 multiple choices, but like it's also like a rush to see if people even finish.
And I hate that. I would hate seeing. So what I would usually do when I would do my in-person exams is I would give the exam to the TA and see how long it took them to do it, and then multiply that number by 2. So if it took my TA, for instance, 23 minutes to do it, I would say that. And the TA is a graduate student who's like super god beast at physics, but I'm like, I feel like an undergrad can at least be half as fast as a grad student. So I would double it. And so if it was like 46, I'm like, all right, cool, we're on the money. But yeah, thinking about it, yeah, maybe the 3-part FRQ would be too much to put into a 50-minute section. So maybe it would be like 1, 1, and 1. I still think I want the 3-part FRQ because it's fun. The FRQs are the more interesting, I say, like your moment to shine type questions, because there's different ways to solve them, and they're scaffolded so they build on each other. Whereas like multiple choice is just like, bruh, it's either like A, B, C, or D. And you're just like, whatever.
I would say, I mean, I also think this class is an accelerated class.
Yeah.
So I feel like it would be very difficult to do a class, or it would be very difficult to give out an exam every 2 weeks, 3 weeks in this class, and have it be the same length and time as other classes exams. Even though it's the same amount of content, it's obviously compressed.
Yeah, it's even like super compressed from a teaching standpoint. I run out of time constantly. You'll notice in lectures, like towards the end, I'm like, oh shit, like we're gonna go over, and that's even me like cutting out a lot of topics that I kind of want to cover, but I just don't have time for it.
Okay. But I guess back onto the exam. So it's
Yes.
8 hours.
Yeah, window will be
same pace.
same pace,
everything.
same everything. Hopefully, Kudu shows the right numbers before and after this time.
Okay, it's still on Kudu. It's still
It's
we
still
can
on
ask
Kudu.
questions on Campus Wire, etc.
Yeah, you're fine doing that.
Still get an equation sheet. We
Mhm.
can still use like our homeworks and if we
Yeah.
have our own homemade equation sheet. Can we do
You
that
can
for
go
the
back.
final?
You can go back through. Yeah, I mean, I can't prevent you from doing anything, technically, but yes, ethically, you can still use your own cheat sheets. You can still go through previous homeworks. You can still even go through previous lectures if you want to. Yeah.
Okay. All right. Because what was it? Because I have a couple of homework questions for homeworks 5 and 6 that I did.
Yeah. Mm-hmm.
And some of them were, let me see. let me look. Let me go look through it. Where is it? Where is it? Homework 5, question. Where is it? Number 10.
Homework 5, number 10. Let me go find it.
Yeah, sorry, my thing is buffering.
You're good. You're good. Homework 5.
Let's see. Like homework 5, question 10. This one was, I guess, like kind of challenging in a way, because like at the end of the day, I knew it was like one force is acting here, another force is acting there, and they're supposed to be like equal. It's just like this one was like a lot of like, I guess, not deriving, but I guess algebra.
Mm-hmm.
And so this was kind of like time consuming. Do you think we'd see something like this on the exam again? Probably.
Oh, is this the 2 beads and 1 beads, and then there's a third bead, and then they... yeah, probably. This is a classic question. People love this one. Let me see. Why is it on the screen not
so I
showing?
should practice one for the exam.
Yeah, I would say so. Let's see, is it 2 beads having opposite positive charges are fixed at opposite ends of a horizontal insulating rod. Yeah, but where's the figure?
I was just supposed. Oh yeah.
This is the one I had to repost all the figures. I got so mad at this. Ugh, okay.
Okay.
And consider a bead with charge Q1 at the origin along the positive x-axis pointing to the right. That's a third small... Dude, I need the figure, dude. I can't even see this, dude. What excuse me? All right. Where'd I do it? Homework 5, missing images. It was question 10, yeah?
Yeah.
Okay, there we go.
Oh,
That's
also, whenever we're doing an integral for like the electric field,
yeah,
is it like we're working at a point inside going out or outside going in?
For electric field, you're usually inside going out in terms of like R and things. You mean when you're doing Gauss's law for like Q enclosed?
Yeah, whenever you're, because I have in a lot of my equations that like it's going, or I guess it's inside, or sorry, it's outside going in.
That's for like potential. Potential, a lot of times when you do like the E dot dr, you want to go from infinity into where like you're measuring the potential.
Okay.
In general. The reason for that, right, is because delta V is equal to negative integral, and then it's like location 1 to location 2 of E dot dl, yeah? And delta V, right, is usually V2 minus V1, right? Final minus initial. So
Okay.
do you see how like potential is always like referenced to something, right? It's always minus something. This is always like the reference potential. I know they'll say like calculate the potential here. Really what they're meaning is calculate the delta V, calculate the relative potential, but then the thing it's relative to is the potential out at infinity, which is the potential of 0. So like
Okay.
usually at infinity, because we say like V infinity is equal to 0. And so when you're doing your integral, right, if 1 is at infinity, so it's negative infinity to like location 2, this is like outside coming in.
Okay. Sorry, I'm reading up for something real quick.
You're good.
Whenever for homework 5, there were a lot of cases where we needed to like derive or like figure out the, not like to use this like the electric field at like some weird shapes and stuff. Obviously, it still have some level of symmetry.
Yep.
But do you think we should do a lot of like practicing those kind of things?
Yeah. We've done them, I think, in class, or yeah, doing, for instance, calculating the electric field. When you have, what is it? It was like a rod of like a certain length, and you had to calculate the electric field here. I think we did this one during lecture. That's kind of like a cool one. Also, calculating the electric field when you have like nested things. So, for instance, if you had like nested cylinders, and I don't know, they could be triple nested. You could have like a third level if you really wanted to, right? These are important. But you can also use what the standard results for are them. What the standard results for them are, if it applies. So, for instance, for spherical things, you don't have to like rewrite the integrals out all the time. You can just be like, oh, okay, well, it looks like a point charge, and that's kq over r squared. Cool, great. I think the other big one is for cylinders. I want to say it's 2k lambda over r. I think this is the electric field due to a cylinder.
Yeah, like I have that down in my equation sheet.
Yeah, you can just use that.
Should, like,
okay. You can just write. Yeah, I'm not gonna make you rederive it. If it applies. So
okay, so I won't have to like rederive stuff. Okay, that's awesome.
Correct.
Because like I understand how to like do it. It's just it's very time consuming, and it can be.
Yeah.
If you don't have a symmetrical object, I'm like, oh hell no.
Yeah. So if it's not symmetrical, I would say also if the charge density is not uniform, you need to do the integral, right? Because then the integral turns it into something else.
Okay, so if the charge density isn't uniform, you have to integrate, I assume.
Yes. Yeah, for sure.
Okay, got it. Number 12 for homework 5.
Okay. Mm-hmm. Yeah, the Taylor expansion one. This is a good one.
Yeah, I didn't. My question was, I haven't like really practiced Taylor series in a while.
I don't think I have it on the exam. I don't think I make you do it.
Okay, because this one cannot be solved without doing a Taylor series.
Yes. It's very cool, though. You should know how to do it. It is cool. Just in terms of, like, in doing physics, like, knowing how to apply a Taylor series is, like, very, very useful. But I don't think I have a Taylor series question on the exam. Let me just check real quick. Yeah. No Taylor series. Yeah. Yes, Raven, I do shake my legs a lot. I drink caffeine. Yeah. You don't have to know how to do that one for the exam, but you should know it in general. It's kind of cool.
Okay. So for like question 12, should I really study this one?
Let me go find it.
Because it's basically trying to find the electric field. Based on finding the electric field at a point, plus the electric field generated by a ring of charge. So there's like a point charge, a vertical distance from the concentric center, and then
you should know how to calculate the electric field from a ring of charge. That is useful to know. But in this case of using the Taylor expansion to convert whatever that ugly to the 3/2 is into something that looks nicer, I'm not going to ask you about the make it nicer part.
Okay, because I understood that there was going to be like a total electric field at some point. So I did like the electric field of the point, plus the electric field of the ring.
Good. Yeah, that's good. That's all you really have to know.
Okay, because I just plucked off the equation, what's the electric field of the ring from my cheat sheet.
Mm-hmm.
So that made it a lot easier. And so I got to that point. It just, after that, when it started getting into like Taylor series, I'm like, I don't know how to do that very well.
Yeah, no, it's okay. Yeah. The Taylor series thing is something that if you ever take like upper division physics, you definitely want to get comfortable with using that.
Okay. Let me see. Do I have any other questions from this one? Oh yeah, question 16. So this one was like just trying to find the electric field at a point.
Yep.
It took me a while to get to one because I was just so confused where it was before I figured out how to find the diagrams.
yeah. That would be useful.
Yeah, so what you want to do is like you want to break down, because there's one particle, I think it is like you're trying to find the magnitude of the electric field at just like one point, and when it's
just
like,
here. Right? They said find the magnitude of the electric field at the location marked by X, right?
Yeah, you just want to find the electric field at a point between, I guess, two charges, or not exactly between, but there are two charges on the same plane somewhere. So
you want to find the contribution of electric field from each one of them, and that will have components, right?
yeah, so it's like an effective strategy to, like, when you're doing a question like this, think of the electric field, because it, I guess, technically is a force.
Yes.
Into like X components, Y components, kind of like how we did in earlier classes.
Yep.
Okay. Should I practice this one for the exam?
Yes. Yeah. You should be comfortable with doing that.
Okay.
And if it's something that it'll make you do it faster, then yes. Yeah, for sure.
Okay. That's okay. And that's all my questions from homework 5. Have you written the exam for Friday already?
Yeah, I've already written it.
Okay. You're not gonna put out like a practice exam or anything like that, right?
No. Yeah. That dude, with the amount of like bugs Kudu is having, I don't want to put any more things on Kudu at this point.
Oh no.
If I put a practice exam and then that starts bugging out, people are just gonna start yelling more.
Okay.
I want this Kudu nightmare to end.
Let me see. So what is this exam gonna go over? Because I wasn't able to make your lecture today because I'm just trying to like do other stuff at the moment.
You're okay. Yeah, today's lecture was, we did like resistivity and current, which I want to say, is it on this exam? Sorry.
I assumed everything covered up until last Friday was on the exam.
Definitely up until last Friday.
Because you would have had like 2 weeks of stuff since we covered waves.
Yeah, let me see. Charges, electric field, potential. Yeah. Yeah. It's I don't think it's anything that I covered today.
Okay.
Yeah, exam 2 is literally what we covered after exam 1 up until last Friday.
Okay.
The final exam will have a lot of what we do this week. And there's like some special fun topics we do on the last week for like day 1 and day 2 before I just do like final review things. So the final exam will be weighted more heavily towards the stuff that wasn't covered on exam 1 and exam 2.
Okay. So would you say, because I'm assuming on the final, since you'll be covering like basically a week and like plus 2 days of content, could I be like 25 being like I guess midterm 1 and 2, and like 50% is like stuff from here until I guess next Friday.
Yeah, sounds like some good percentages.
Okay. Okay, that makes sense. Let's see. Question 5 on homework 6. This was like trying to find the flux for like point charge, I think, but it was not a point charge, a cube. But the
6,
point charge was
question
on a
5.
corner of the cube.
Oh, yeah. This one was tricky.
I was confused because it was like, obviously I want to make a cube here, or not a cube, but like a, what kind of shape was I trying to make?
Like a sphere, maybe?
Yeah, I think probably
Find the
so.
magnitude of the electric flux through the shaded face, yeah. So, I mean, here's the important thing, right? Is that, E.dA is equal to Q enclosed over epsilon naught, where this is also equal to, like, the total electric flux, right?
Yeah.
So the problem is that, like, the charge being on a corner here, this cube doesn't enclose all the charge.
Yeah.
If you wanted to think about it, it actually only encloses, like, I guess like an eighth of it, maybe, right? Because it's a quarter of the top hemisphere, and then there's 2 hemispheres.
I wasn't thinking of that whenever I was doing the problem. I thought the total charge was just like inside the cube in a corner, but
Yeah. The problem is, like,
doesn't make
if it's at the corner, right? It's still exerting flux out this way as well, right? So this amount of electric flux isn't getting captured by this integral.
okay, yeah.
So what you do have to end up doing, this is kind of it's a cute trick, is you build a bunch of cubes around it. And you say, okay, well, how many cubes would I need in order to enclose the whole thing? In that case, I guess it would have to go down as well, right? Yeah. Because you need to cover the bottom part as well. Yeah. Is that the way they want us to do it? Do you put a third
Yeah.
one out? Is it a 3x3x3?
It's a 2x2x2, but
2x2x2.
so that captures all of the charge, but then it wants you to find the ones with the shaded faces.
Right, yeah, and so you have to ask, okay, well, how much of the area is just this one shaded face, right? And so there's 6 sides to a cube, and each cube has 4 of these squares. So then one of them is 1/24th of the area.
Yeah, so you get 8 cubes, and then each cube has, let's see, I guess 3 sides that has flux going through it. So, okay.
Well, wait.
8 total.
No, there's 24 total faces, right? Well, there's 6 faces.
There's
but-
8 cubes, but only 3 faces of each cube is getting exposed with flux.
No, I don't think so. Wait.
Because it's only asking what's the flux for that one surface.
For this one face, right? Yeah. So wait, this whole surface has flux coming out of it. This
Yeah.
whole flux has surface coming out of it. This whole flux has surface coming out of it. Sorry, this whole surface has flux coming out of it.
Yeah, and that's 4 on one
Times
side.
6, right? So there's 24 of those, but we want only one of those cubes. So that's
Yeah,
why
so
it's
only
1 over
one.
24.
24, yeah.
Yeah.
Yeah, okay.
Technically, all the cubes have flux going through them, but that's the electric flux just due to one side, one of the faces.
Yeah.
Now, this would be terrible for measuring an electric field, right? Because this is not symmetric, right? This face is like not the same distance as the top face. So you can use it to calculate the amount of flux. You can't use it to count the amount of electric field, because now you're trying to map a spherically symmetric electric field to a cubic surface, which that doesn't make any sense. The whole reason Gauss's law works is that the surface, the Gaussian surface you're using, has the electric field being constant along that surface. So that if you wanted to solve for electric field, you can like pull it out so that it's E. So this is a constant in regards to the surface area integral, and then this literally just becomes the surface area.
Okay.
Khan Academy. Not quite.
Question 11 on this homework.
Okay, question. One second, I'm reading the chats. Someone said, both ways of calculating arrive at the same results. So the first method of saying 6 sides in the big cube each contain 4 faces, whereas the person on the voice chat, which is you, said 3 active faces for 8 cubes, 1 cube at each corner. Oh, okay. 8 for 8 cubes, 1 cube in each corner. 3 faces being outwards, both being 24. Okay. 3. Oh, I see what you're saying. Okay. Fascinating. Okay. All right, sorry. Which number was it?
Number 11.
On the same homework?
Yeah.
Oh yeah, this is a fun one.
Should I definitely look over this one?
I think
I know
so.
I keep asking, but
He's like, I'm baiting you, dude. I'm baiting. Yes, I mean, you should definitely look over this one, because I have a feeling that even if this one isn't covered on here, I think it's also covered on the final, maybe. I do like this question.
all right.
Okay.
So I'll probably see something similar to this on the midterm then.
Midterm or final, I forget which one it was, but yeah. I'm not legally binding, but just it's a good question to do. Do you know how to do this one?
I knew how to do the first part where like what's the Gaussian surface up until like the outside of it, right? But then I was like, okay, I can get.
Well, this is weird. The whole cavity thing. The way to treat this question. This is a cool trick. I didn't go over this during lecture. I didn't.
When I looked it up online, it was like you should give the cavity, the circular cavity, like its own electric field or something like that. And
you
then
should
just make it like.
You should have it
the
have the opposite charge. Yeah.
Yeah. Make it like a negative like charge density.
Yes.
Or something like that. That just subtracts the space.
Yeah. For instance, if this is like positive rho, then this one needs to be negative rho. Okay. And that gives the effect of having a cavity of like there's no charge. And so if they want the electric field at a point P, right? Okay. So in that case, I think you take what the electric field would be due to the blue thing at point P. So here, let me draw that. Right, and then sorry, and then we're figuring out at point P. So A, R, whatever this is, point P. So you first calculate what the electric field is just due to the blue at point P. And I believe that, right, so that's E times, we're going to say 4 pi r squared, right? Is equal to the charge enclosed, which would be 4/3 pi r cubed rho, right? And then over epsilon naught. See how this would be charge enclosed?
Yeah.
Okay, good, because it's volume times density. Okay. And then that points in the r hat direction. That's the important thing. That points in the r hat direction. So if we're measuring here, electric field from this points that way still. Okay, then you have the electric field due to the red part. Which... Oh, I need a different color. What color do I want? Let's make it brown. Okay. So this is now your new, like, R, per se, okay? But that vector, right, is equal to R vector minus A vector, right? You see how A vector plus whatever this, like, I don't know, we could call this, like, R negative vector. That equals big R vector. Let's call this, like, R minus.
Yeah, when I got everything up until this point because I was so confused. Like, how do you solve for that? Because, yeah, I didn't think to do that.
Yeah. You want to relate these two because eventually you got to do something with this.
Yeah,
So
because I
then
understand you have one electric field from the solid sphere, and then you have another electric field from the, I guess, the negative anti-cavity, whatever.
Yeah.
And he was just at some point. Obviously, you're going to have two electric fields acting at that point P. I was just didn't know how to relate them.
Yeah, it's one of these things, like, once you've seen it, like, it'll make sense when you see it again. But then this was, like, rho minus, right? Or we say, like, negative rho. And then this is still R vector minus A vector, and then that's, like, whatever that is, like, hat. Okay. So this is, like, the magnitude, right? I'm having to write it as, like, magnitude of vectors. And then, so when you subtract these two, right? Because you have to, well, you add these two, right? You add this plus this, but this has a minus sign on it. So here, let's simplify what this is. So this, the 4's cancel, the pi's cancel. You get r squared, r cubed over r squared. So that's just going to be r hat. And then it's rho epsilon naught over 3, right? Or rho over 3 epsilon naught. For just doing this part. So cancel the 4, cancel the pi. 3 goes on bottom. I still have a rho. And then I have r cubed over r squared, which is just r. And then I still have r hat. Okay, and then that's minus this. So again, r minus a squared. And then r minus a cubed. So you're going to have... And still 4's, pi's. Still going to have 3 epsilon naught. And then this is going to be r minus a magnitude. Just a single one, right? And then there's still a rho. And then this is r vector minus a vector hat. Okay. And then this is the key thing, I think, is what they figure out. Is so r hat is the same thing as r vector over r hat is the same thing as the vector r divided by the magnitude of r. Okay. So r hat times the magnitude of r is the same thing as just the vector. So when I see this right here, Jack, like the magnitude of the vector times the hat of the vector, the unit vector, that's just the regular vector. And so this becomes 1 over 3 epsilon naught. There's still a rho on here, I guess. And then this is going to become just r vector. And then minus, I still got the 1/3 rho of epsilon naught. But now this is going to be, since this is the magnitude, this is the unit vector, this is going to be minus r vector minus a vector. And then here's the cool thing, right? These cancel. And so I think you just get negative rho over 3 epsilon naught a vector. Is that what the answer choice was? Yeah. Oh, they wanted just the magnitude. Right. The field strength. Okay. So then it's just A. Uh-huh. Right. And then the magnitude of that is just negative rho over 3 epsilon naught A. Whew, that's kind of a pain, that question.
Yeah,
But yeah.
left and right. Can I write that down for a sec?
Oh, for sure. Here, I'll download it for you too. I'll put these on Campus Wire, so you can have them as well. I won't put your name on it. I'll just say that these are just questions we did. Fuck, which one was this? Sorry. Question 11. There, I'll leave it for you. While I go find it. What's up, Sarayam? I think this was homework 6. Was this homework 6?
Yeah.
Okay, cool. Okay. Cool. Any other questions for this?
Let's see. No, I think that's it for this homework. I still have to get a little more caught up on the stuff for the exam, but if you had to like put your finger to it, since you've written the exam, what should be like the coverage of topics?
So Gauss's law for sure. Electric potential.
All right.
Coulomb's law, right? Like figuring out like forces. And capacitors. Yeah, I would say like capacitor circuits. You should be good at like how to find the equivalent capacitance from like a bunch of different capacitors in various like series and parallel arrangements.
Okay. Would you say that's all like a 20-20, like a 25-25-25-25 split?
I can do my thing where I just go through the questions and tell you what the topics are. I can do that too.
That'd be awesome, yes.
Let me just go see one sec. Sarayam, is a 4 on AP Calculus BC a good score? It is. Yeah, good job on AP Calculus. Your old account got put on timeout. If your old account got put on timeout, Sarayam, it's probably because you were spamming and one of the mods eventually got fed up of it. That'll happen. Okay. Let's see. Yeah, Gauss's law. Electric flux. Potential. Oh, we did do resistivity. Okay. Yeah, I take that back. There is something from today on the exam. So resistivity.
Okay. Is resistivity only going to be covered today and tomorrow?
Oh, we just covered it today. That was it.
All right. I'm guessing that's question 3 then.
Oh, question 4.
Okay.
And then, yeah, electric potential energy.
Alright.
And then more electric potential energy. And then capacitor circuits. Capacitor circuits. And then one of the FRQs is... Gauss's law.
Okay.
And then the other one is Gauss's law. Plus potential, plus capacitance. So it's like a question that incorporates all 3 things. Like basically, you use like Gauss's law to figure out the electric field. And then you use electric field to figure out potential. And then from potential, you can figure out capacitance.
Okay.
Yeah. Mathematician, what's my name? Sensation Bandom. Oh dear, Sensation. Some of the mods in my channel, dude. I used to be on timeout, now I'm banned.
So Gauss's law, that has to do with obviously Gauss's law and Gaussian surfaces.
Yeah.
Electric potential, that's stuff from like homework 7. Like, is that like electric potential energy and like voltage?
Yes.
Okay. Okay. Then you have Coulomb's law and like electric flux.
Mm-hmm.
That's question 2. Okay. Capacitance and circuits, that's like question 8. Well, I mean, yeah, I guess question 8 because circuits. Or not question 8, but homework 8.
Yeah.
Okay. And resistivity, is that, it's only like one question, but is it like really integral and stuff like that?
Resistivity?
Yeah.
What? Sorry, what'd you say? Is it what?
Resistivity is, what is resistivity? Just like the resistance of like wires?
It's related to it.
Is it like V equals IR?
Eventually, that's like one of the end products of it, but no, resistivity has to do with like current and area. Yeah, I think resistivity is current divided by area.
Okay, got it. Okay, thank you. Will you be having like a review session Thursday or Wednesday?
I'll do another office hours for sure on Thursday. I don't know about like review session, but if you want to like lead it and just like keep asking things, sure.
Okay, got it.
Yeah.
That'll be a big help.
Yeah, we will for sure for the final. I have structured like reviews that I'll do.
All right, got it.
At that point, it's a lot of topics, and I want to like just briefly cover everything. But for the midterms, I'm kind of just like, eh.
All right, got it. Thank you very much.
You're very welcome. Mathematician, I do know who you are. Am I tutoring anyone? No, that was just office hours for my UCLA class. Someone was asking some questions about the upcoming exam, and they wanted some help on things. Kaushik Techno, I do know you, Techno. What's up, Dr. Gold? What's up, Kaushik? Sorry, I am a Dr. Gold. Bro's getting fed up with the questions. I'm not fed up. I'm just tired. Let me see. What did people submit to the queue? Sorry, I probably don't have any time to go through the other queue today. I was explaining that this class ends on the 31st, so then I will get back to having more time to answering more viewer questions. Just for my job, I have to answer UCLA questions first. Let me see. Mango Sticks, what'd you have? What'd you have for me here? Ooh! This is actually, but this is a UCLA question, actually. Yeah, this is a good one. Let me do this one for you, Mango Sticks. I don't think I covered this in lecture. Well, we covered dipoles a little bit. Yeah, no, for sure, for sure. No, you're okay. Yeah, this was potential though, right? I think I need the potential due to electric dipole is placed in a uniform field E, where E is parallel to P. One of the equipotential surfaces is a sphere. Find the radius of the sphere. So that means the potential everywhere is constant. It's a good one, Mango. Let me go find it. Wait, this homework was due today? Really? Due tomorrow, probably. Isn't today Monday? Homework's due on Tuesday. No, you're right. Homework is due on Monday. Ugh. Yes. I think that would be this. Yes, UCLA. Mathematician, you're right. We're gonna do potential from a dipole. Could have sworn I did it here somewhere. There we go. The electric dipole. All right. What SAT score do you need for UCLA? That's a joke. They don't look at your SAT score. They should. Okay, remember this is... $2,000? No, that's back when we took the SAT Sensation. They don't... It's at a 1,400 again. Or 1,600, sorry. Okay. Dipole P... Oh, sorry, this is on question... Was it question 10 of this homework? Uh-huh. What was the solution to this? Yeah, okay. Okay. So if you have a dipole, which has a dipole moment of P, then the potential created from that in the r hat direction is, well, P dot r hat. So I think we're going to look at this, for instance, being like our r direction. And so the potential here, so V for the dipole, and again this is at the origin where this is like 0 0. The potential at a point P due to, yes, okay, so that's equal to K, and then so P dot R, we assume the dipole moment's pointing the same direction as this. Oh, actually, I remember how this works. This one's actually tricky. Yeah. P dot R hat. Right. Oh, no. Okay, so. Uh-huh. Okay, I see. So actually, the potential anywhere spherically. No, but it's a dot product between these two. Chat's going crazy. Sorry. Okay, so I think this is P cosine theta, I want to say. Or, okay, I think I remember what we do here. So P to R hat over R squared. Let's just leave that for now. Potential due to an electric field is going to be equal to K. Or actually, no, right? So potential over distance is equal to electric field. So in this case, and the electric field points parallel to P. Let's say P just points up. That means the electric field is like a distance Y above this, right? So I think it's the same dot product, is it not? So V is equal to E, I guess, times Y. Or let's say like ER. But it, I want to say EY, I think. I think it's this. But then I need to add these two to get what the total potential is. But then I want the total potential to only depend on R hat. Yeah, this is the tricky thing here. Yeah, okay. Let me think. I want to say it's R dot P hat, maybe? Let's see, what do they have here? What do they have a solution? Oh, and it's also negative. Okay, sorry, I forgot it was negative. Let me make sure I have that right. They have them aligned on the x-axis, whatever. Sensation, please chill with people in the chat, dude. Or else I gotta take your mod powers away. Okay. Okay, I think it came from this. One sec. So P dot. Okay. And then this is the amount in the, I'm going to say this is in the y direction. Right, okay. So let's assume electric field's pointing that way. P is pointing that way. Let me rewrite, like, R vector, right, is the same thing as R hat. So R hat is equal to R vector over R. Okay, so then I can rewrite this as K. I assume this is supposed to be P vector, not P hat. What do they have? How do they describe this? Sorry, within the textbook. KP R vector over R cubed, which they're writing as one sec. Don't worry, I'm not gonna ask this question on test. This is kind of a mess. I hate that this doesn't have the right things on it. VP, KQD, P. They should have written this as a vector, not just as like a regular letter. Is P? Let me get something better. I don't like this kudu definition. It should be normal scalar, right? Yeah. Yeah, R hat is a scalar vector. Yeah, you're right. I think that's what I want. Okay. P dot R hat, I think, is gonna pick out P times Y. Yeah, I think it's gonna pick out P times Y. Yeah. But where are they getting R cubed on the bottom? Unless this is wrong. What's up, Alistair? Okay, I think, okay, P dot R hat, okay, wait, is equal to P times 1 times cosine theta. How are they getting an R cubed on the bottom? I don't determine the adds. Right, okay. This is fine. Yeah, P cosine theta. Oh, I think I know how this works now. Okay, wait. 1 sec. Sorry, this is a little bit of like tricky, like Calc 3 stuff almostly.
My name is Jeff.
What's up, Jeff? Good to see you, dude. Okay. I'm just doing office hours right now for a student. You never get ads here. Good. Okay. P to R hat is the same thing as P times the magnitude of R, which is 1, times cosine of theta. Okay. I think this is where I want to say. Okay. But Y is going to be equal to R cosine theta. So this part, so P dot R hat is equal to P over R cosine theta. Or no, Py over R cosine theta. Yeah. Stokes theorem. Zach's pretty good at Stokes theorem. I'm about to end the stream. I've been going a little bit over time because Mango had this question. Okay. So, yeah, okay. Because P is pointing up, which is in the Y hat direction, in the Y direction. P dot R is gonna pick out the amount of R that's in the direction of that's in the Y direction, which is why you get this. Y over R is equal to cosine theta. So now I can substitute this in for here. And I'm going to get that P dot R hat is equal to Yeah, no. You're totally right, WW. It is kind of weird, right? So, here. So, the potential, right, from this now becomes KPY over R cubed. Okay? Whereas the electric field is just going to be equal to negative EY. Okay, then let's add these two. So if the dipole plus the electric field potential is an equipotential, this must be equal to a constant. And so I'm going to get KPY over R cubed minus EY is equal to C. They kind of lead you with the question here because they said we want to write the potential at point P. Sorry. We want to write it as the radius of a sphere. Yeah, and the field due to a dipole does look kind of weird and curvy. Okay, so this is for equipotential. I need these two things to be a constant. Okay, so let's rearrange for R. So I'm going to get that EY over KP. So if I move that over and divide by KPY. All right, sorry. No. It's C plus EY. And then this is all going to be divided by KPY. And then it's all, yeah, okay, right? Okay, cool. So then R is equal to C over KPY plus E over KP, all to the 1/3. And then I need R to not depend on Y if it's an equipotential. If it's an equipotential in the shape of a sphere, right? Right, because a sphere has all sorts of different Y's. This looking like a sphere could have like y equals 0, y equals like a half, y equals 1. So I guess C must be equal to 0. So C must be equal to 0. So it's an equipotential of potential 0. So R is equal to E over KP to the 1/3. Is that what the answer choice was? Yeah. Well, I have it flipped, I think. Well, that's... I do have it flipped. How do I have it flipped? Oh, I know what I did. Sorry. This was R to the -3. Sorry. -1/3. Sorry. -1/3. So R is equal to KP over E, which is equal to 1 over 4 pi epsilon naught P over E, all to the 1/3. And that, I think, is the correct answer. Yeah. Yeah, there you go. Okay, cool. Yeah. All right, let me see what... They're behind a paywall, but they're mostly from OpenStax. You got it now? Okay, great. Sorry, yeah, this one is kind of a mindfuck, honestly. You have to like do like some funny things here, and they're kind of leading you on because they say that it has to be a sphere. So you're already solving for R, I guess. I think it looks like a bean if I remember. They come back down to the negative charge like a perfect oval-shaped bean, kind of with 2 notches. Yeah. So this is... Here we go. Wait, but potential doesn't have direction. Potential scalar. Dipole scale. Yeah, it's scalar, right? These are field lines. Yeah, okay, here we go. Yeah, the arrows are field lines. Purple represents the highest potential, yellow is 0, and cyan is the lowest. Okay. So in the presence of an electric field, potential goes from like from either like positive to negative, or you can think of like 0 to negative. And so some distance away from this. Yeah. I don't know. It's a really weird question. Oh, you did? Let me check. Sorry. Right. Oh, and that's the potential. The equipotential lines is what you're drawing here. Yeah. So in this case, the red are the electric fields, but then the green are the equipotentials. And so this is like positive potential. I guess this is like negative potential. Yeah. But then it's right, it's KQ over R. And so then if you have an electric field, and so and then dipole moment, right, points from minus to positive. So P points this way, but then they also said the electric field points this way. I see. And so the electric field points from positive to negative. So I think at a certain radius, somehow here, the amount of like positive here cancels out exactly the amount of negative here, and the amount of negative here cancels out exactly the amount of positive here, and it makes it a sphere. Super weird. I don't know how that would work.
Emotional, damn it.
Okay, my brain hurts. I can't do anymore. Let's close the stream out. All right, thank you everyone for coming to Actual Education Office Hours today. Yeah, it would be super cool. Yeah, I wonder if there's like a little bit of Desmos there that we could like throw something on Femvox. Yeah, I don't see how we get a sphere either, but apparently we do. Anyways, office hours tomorrow is gonna be earlier. I'm gonna only have it for an hour because I gotta go to this AAPT conference, but I will still stream. So tomorrow at 11 a.m. we'll have office hours. If any of the physics students want to come by, ask questions. If there are no physics students asking questions, I will go through and solve any other cool questions that have been asked. I know the queue's quite long at this point of different things, but I can mark Mango Sticks is done at least, right? Mango Sticks. We did do yours. $10 if you put this on their exam. Oh dear. What were you gonna do? You were gonna give them inductors with currents and a voltage source, and is that a current? No, I don't know. Yeah. Oh yeah. We're not doing network problems. That's like an EE question. It's fun though. And then I did do this one. Okay, so we did do that one as well. Let me just clear the queue a little bit. Do you need to still do Laplaces? Yeah. Gladiator, I will get to this at some point, sorry. And we didn't do these two. Okay, I'll just leave them on the board. We'll get to them eventually. Okay.
My man.
Anyways, yes. If you want to find out when we're streaming, there's a website. I know Zach's maybe doing a 16 game this weekend. Should be fun. Little trivia game. And then there's all sorts of other fun people are streaming. Let's go raid somebody. Who do I want to go say hi to? Let's go say hi to Moo. I haven't said hi to Moo in a bit. So, we're going to go say hi to her. Alright. Enjoy the rest of your Monday. We'll see you around. Peace.